Have you ever had to abandon a design because it didn't work, even though you got a lot of the small details right? Or maybe the machine you designed works, but it's just not as useful as you thought it would be, and it doesn't end up being used much, and maybe over time used less and less until nobody uses it. Well, if you had an experience like this in the past, then this podcast is for you. Because it turns out that designing a machine is actually a lot easier than it seems like. So today we will go over the single most important question you need to ask yourself before you sit down and design a machine. And ultimately, asking this question will greatly increase your chances of designing a machine that actually works and gets used. But here's the thing, if you don't ask this question, then it can cost you hundreds of hours and thousands of dollars. And worst of all, you get a machine that doesn't work and potentially just is scrap. In fact, I'll share an example with you where there was a machine that was scrapped that probably cost close to $1 million. And all of that was because not enough time was spent in the beginning asking the most important question before engineers jumped in and started designing the machine in CAD. Welcome to episode 3 of the Engineers Grow podcast. My name is Andrei Salfetnikov, and I'm excited for today's episode because we will be talking about the question that is probably the most important question you need to ask when beginning a new design. And that's because this question has such a big impact on the design. So let's dive in. And the single most important question is, what does the machine need to do in order to work? Now, I know that's super simple, super basic, and it seems like, wow, that's such an obvious question. But the reality is, oftentimes we're in a rush. There's a lot of pressure to design faster and faster and faster that we can make a lot of assumptions. And we can start assuming things what the machine needs to do based on what he said, what she said, but what those people said, what that manager is asking you to do. And so there's all of these people with all of their expectations. And so it's easy to start making assumptions. But it's important to step back and really ask that question. What is the minimum that this machine needs to do in order to work? Because, there's a lot of things. You can probably list 10, 15, sometimes 20 things that the machine needs to do. But in reality, there's probably one or two most important things that are the whole point of the machine. And if those one or two things don't work, then there's no need for the machine. Everything else is to support those one or two main tasks. So that's why it's so important to ask this question. And then the next follow-up question is, what do I need to do so that I can quickly and cheaply test this idea and make sure that the machine can actually do what we need it to do? Now, the whole point of this is to not design a whole machine up front and then test it, but start doing some prototyping, some testing with as cheaply as you can, as quickly as you can, to validate all of your assumptions. Because you might assume the machine needs to do this and that, and then it will work. If I design A in, and if I design this bracket here, and that mount there, and if I use that motor there, it will work. But maybe it won't. And you need to figure that out as soon as possible, because for those very critical functions, they might be hard to update down the road. So if you can find an answer of whether it works or not early on, you can actually design a machine that works. And so, yes, it takes time. You kind of have to slow down. Sometimes there's a lot of pressure to get it done fast, and you kind of have to be able to kind of handle that pressure, but at the same time find a way to work with the team and with managers and project managers to kind of slow things down and get some time just at least to do one or two, if not more, experiments, tests, quick and easy prototypes to check for those critical things the machine needs to do. And then once you get an answer, you can move on. So that's kind of the summary. That's the one question, most important question you need to ask. Now, let's move on to a few examples where I'll show how that question was asked and how it was used and the results that were achieved by asking or not asking that question enough. So example number 1, and this will be example of pretty much an example where you avoided a loss. And so in this case, we have a machine, and I can't talk about exactly what it does, but basically it takes a component and it modifies it. And so kind of the big constraints I had to work with on that machine was, one, I only had $15,000 budget. So all the materials, all the parts we ordered for the machine, they had to cost $15,000. The other thing that was important about that machine is that it needed to have precise motion in the horizontal direction. So there were some parts it had to move, across the table, and that position had to be very precise. Now, with this idea and with this machine, a lot of people on the team already wanted to use it. They were getting ready to implement it into production. The idea sounded really great for what we needed to do. And so there was a lot of pressure to go from an idea straight to a production machine that we can put on the production floor and start using, and where our technicians can start using, where things are like semi-automated and a lot more simple, where there's not a lot of engineering thought into it. To build a product, the technicians, they just have to go in, follow simple instructions, and just press a few buttons, and it does all the motions for you. And of course, they wanted it ASAP. Like always, we are always late because we needed the machine yesterday. The other few things that were important about this machine were, like, there was some safety concern. We were involved. There were some flames and stuff. There were some gases we had to work with. And so those had to be addressed. But what was the problem? Well, the problem was that the budget was just way too small. We were given $15,000, but after we started adding up all the components, we'd probably need closer $30,000 to $50,000. And so that was a big mismatch. Basically, we needed 2 to 3 times more than what we had. But it sounded like there wasn't going to be a lot of leeway right now to increase the budget. But there was actually a bigger problem. The bigger problem was that no one actually tested yet if we could even do this. Can we even modify the part in a way that we want to modify it? Now, we couldn't do it earlier, so that's why it wasn't done. But now the idea was, well, we wanted to jump from an idea to a full machine, and we didn't have the money to do it. So we had to go back and ask that question: what does it need to do? What are the most important things, and how can we test them early? And we broke up the project into multiple phases. Basically, one is the quick prototype and test to test out the idea. And our hope was that if we go at that once or twice, and we're going to run out of money, but at least we'll have a way to prove that it works, and then we can use that to get more money for the project. But I'm kind of jumping ahead. We decided to quickly test the idea, so we ordered some COTS parts, like we ordered some linear stages, and we made sure that, that was like one of the bigger expenses on our list. So we just made sure that we can use it for testing, and then once we're ready for production, we can use those same stages in production. So we figured out what stages would be best for that. And then everything else we could was 3D printed from plastic parts using an FDM 3D printer. Now, there were some parts that were metal. They had to be machined, and other materials, actually. And we were able to do that in our internal model shop. And there were a few covers made out of sheet metal, so we had to get those made out of sheet metal. But pretty much we were able to stay within our budget, which was a little tight, but for a prototype and an engineering type station, it was going to be good enough. So what result did we actually achieve? Well, we were able to get a machine that the engineers were able to use. And actually, we actually got it pretty quick. I think it was like a month and a half or so is from when we started working on it to where we had parts and a machine assembled to where we could start using it. So that was great. But the bad news came soon after, when the engineers that were working on modifying the parts, they tried many different things, but it just was not possible to modify the part the way we wanted to. And so we had to move on to a different approach. So, I mean, it might seem like, oh, that was a failed project, but going back to that question is, what is the most important thing and how can we test it quickly? It really paid off because one, we still, we only paid, $15,000 for the parts and a small amount of hours to actually design the machine. And then it turns out it didn't work. So that's all we spent. Whereas we could have spent $15,000 to $35,000 more if we tried to go and straight into a production machine. So this is a great example of when you slow down and you do a prototype that's cheap and is quicker to put together. Sometimes you can avoid going down and designing a machine that's actually not going to work regardless of what you do. And that would have been a much bigger loss than it was by testing a quick prototype, which means now you have other money. The money that you would have spent on this wasted machine could be spent on the next idea, which can actually work. And so whenever you can do that, it is always a great idea to do it. And this works well on budgets like this one, or smaller budgets where maybe you're dealing with hundreds or thousands of dollars, or on the other side where it's bigger budgets, tens of thousands of dollars. So this worked out well, and it was a bittersweet moment, but it was definitely worth it. Now, let's move on to example 2. But before we move on to example 2, let me know in the comments, what machines are you working on? I love to hear about what different machines different people work on. So with that, let's move to example number 2. So an example number 2 is also a good example. And in this case, it was a fixture that needed to help with cleaning some parts. And it was actually a much smaller fixture than the machine that we're talking about earlier in example 1. But it illustrates how many projects, probably a majority of projects, would go when asking that most important question: what does the machine need to do? And then how can I quickly test and check that actually I can do that? And so in this example, this fixture, you would have to hold some components, some parts, and then you'd have to lower it into a cleaning solution. And then after they're done cleaning, you have to raise it. And, like always, we needed a solution ASAP. But what was kind of different about this fixture is that most of the need for this fixture came out of ergonomics. And so currently the technician would have to, manually put the parts into the cleaning solution, hold it for a certain amount of time, and then pull it out. And it wasn't the most ergonomic setup. And so there were some concerns around it. And so that was the problem, is we needed to replace that fully manual way with a semi-manual way where the fixture provides some control of the motion and is able to hold the parts in place at the different spots in the cleaning position and the top position where you're loading or unloading the parts. And so once again, following that same methodology, we ordered cheaper COTS rails and 3D printed all of the parts that we could to test out the fixture. So what results were we able to achieve by having this cheaper fixture to start with? Well, a few things. One is we discovered several issues with the fixture. One of it was that, these rails, for some reason in the vertical motion, they just didn't perform as well. And they were pretty rough to the point that they were very hard to use. The other thing we ran into is we found that aligning the components was a lot more critical than we thought it would be. And it seemed like the operator was able to do that pretty well. But for some reason with this rail, it just wasn't working out as well. But there were some other interesting findings. Like when we were looking at the fixture at first, we thought, it needs like a locking up, and say it needs to be here or this part needs to be there. Well, once the technician started using it, we started realizing that, it would actually be better if the locking nut was here And if I didn't have the stop there, or the stop would be here instead. And so we were able to learn a lot of about, the real requirements for the fixture, about how to use it best, basically. And so by having this cheaper fixture, we were able to, figure out what does the more expensive fixture actually need to do. And so that's what we did. We replaced the cheap rails with nice linear rails, and then a lot of the 3D printed parts were replaced with metal parts. And then also we updated the design for all the little changes the technicians proposed based on where things like knobs and stops should be located. And so by learning that on the cheaper fixture, we were able to get the more expensive fixture right. Not the first time, but obviously the second time, without having to change it again. So this is actually probably a typical example of how often asking the right question works out. You ask it, you do some testing, you find some things that work well, some things that don't, and then you iterate. And sometimes it takes one iteration, like on a more simple fixture like this, or on a bigger project, a bigger machines, it may be multiple iterations that you go through, each time getting to a better and better design, and oftentimes buying, more and more expensive parts as needed, because then you actually know that you need them there, but you don't need a more expensive or a more rigid or a more strong part over there. So that's kind of how this example illustrates, what happens oftentimes with many projects. So with that, we're ready to move on to example number 3. But before we do, I wanted to share with you in a project that I'm currently working on, and that is a cheaper tool changer for 3D printers. And the whole idea behind this project is to make 3D printer tool changers more affordable to people so that more people can buy them and print multicolor and multi-material prints. So if that project sounds interesting to you and you actually want to go in and build your own tool changer, and you would like to be part of a community where people can ask questions from each other that are actually building it and seeing what they're learning, the issues they're having and how they're able to overcome it. If you want to be able to get on calls where you can ask questions from me of what I'm able to do and things I've learned and challenges I've had and how I overcame them, then I'm planning to launch a membership in the near future where we can do just that. So if that sounds interesting to you, then go ahead and join the membership waitlist. And if you sign up, I'll give you STL files to the latest design that I have released so that you can start looking at the design and see if it's something that can work for you. And with that, let's move on to example number 3. And in this case, it was actually a larger automation machine. Once again, I can't talk about the details, but pretty much at a big picture is that it needed to automate a very labor-intensive assembly step. So this step took a lot of time. It took a lot of skill from the technicians to do just right. And small deviations, small imperfections led to a lot of issues, and oftentimes they had to throw away expensive parts. And so the idea was that if we automate the process, then we can resolve that. Now, when I say we, I mean the company. I actually didn't get a chance to work on this project. I wish I could. It was a really cool project, but I was not able to. So with such a problem at hand, it took a lot of thinking and design time and discussions and reviews to figure out what needs to be done and how to find a machine that, is able to automate that step. And after a long time of designing and building, the team actually found out that the machine was not able to complete the assembly step anywhere close to how good the manual method worked when a skilled technician was doing the job. Now, there were many software and many mechanical improvements that were thrown at the machine to try to get it to work. Different engineers were put on to try to fix it, both software and mechanical. Some even experts were called out to try to kind of get the machine running. However, nothing seemed to help. And eventually, the project was scrapped. And the sad part is, I wasn't involved with all of the cost and stuff, but just by looking at the machine and seeing how much time went into this machine of engineering design time, this machine probably cost close to $1 million for the company. And it is just really sad to see that it got scrapped. Now, later on, I had a chance to talk with one of the engineers that was working on the project towards the end of it. And I asked the question of, what were some of the issues? And it seemed like the big question was no one really fully understood everything the technicians were doing during that assembly step. And so because they didn't fully understand it, they couldn't design all of that in. And then when they had the design working that they built up, and they tried to do the assembly step, it just wasn't working because it wasn't doing all the little things that the technicians were doing. It was just a very complex step. And so all of this leads me to ask the question, well, was this idea even possible? And well, maybe it was possible to make this work, and it just the wrong design was selected. But maybe it's not possible. Maybe the assembly step is just so complex with so many variables that the machine that you would need to design to make all of that work is just going to be so expensive that it's just not worth it. It's just cheaper and faster to have technicians just assemble the machine manually instead of a machine that does it fully automatically. Now, but it does, illustrate that sometimes the idea you want to do is just not possible. And there are multiple ways to find out. In this case, the team found out when they tried to design a production version right away, and they tried everything and it couldn't work. But there would be a better way to design it to where you don't even end up designing the whole machine. What if the engineers, they slow down and spend more time with the technicians trying to understand everything that goes on? And maybe as they put some requirements together, they put together a little prototype and roughly tested it, and then see what results they get. And maybe they make some tweaks and test another prototype and do that several times until they get to a solution, or if there is no solution, till they just figure out, well, there's no way to do it. We don't think it's possible within that makes financial sense. And so in that case, maybe all of the testing, the prototyping would have only cost maybe $25,000 to $100,000, which is a lot less than spending $1 million on a machine that doesn't work. And so I'm not saying that would have been possible, but sometimes just asking that question can mean that the answer doesn't change. It might still be impossible to do what you want to do, but you will find out a lot sooner and after spending a lot less money. And then that's a good position to be in, because then you can stop working on that idea and just throw it away completely. Or that's money that you have left over that could be put onto another project that could be a success. So this example is kind of like a warning in a way, and an example of what happens when you don't spend enough time asking the question up front and doing all the testing you can to validate it. And only once you validate it, then you move on to designing the production version of the machine. That's often hard to do. We're often in a situation where there's schedule requirements and we have to do something quickly and now. And we don't really, feels like we don't have a choice but to just start designing. But if you can even do something like, sometimes we do things in parallel where we start designing a machine, but then in parallel we start working on a prototype just to validate it, so that at least we're making progress on the production version, starting out, on the layout, the main concepts. But in the meantime, we're also not forgetting to test out the critical ideas. Well, so that wraps up the 3 examples we were looking at today. And so basically, the most important question to ask is, what is the most important thing the machine needs to do in order for it to work right? And then once we identify those, we do as many tests as quickly and as cheaply as possible to make sure that the idea will work. So that's the first and most important step to design a machine that works. But how do you take it from the idea and then into an actual machine that you can use on the production floor or you can sell? Well, you need to follow the 5-step design process, which you can watch in this video right here.